Hi again. So this is Nuclear Physics Lesson 10. Yeah, Lesson 10. Binding energy and binding energy per nucleon. So this is A-level physics. If you're doing GCSE, well, you want to hope you're a genius. Right, so first thing I want to do is, we touched on this at the end of last lesson for the energy mass relation. We're going to find the energy equivalent in mega electron volts of one atomic mass unit. So atomic mass unit, remember, is on the data sheet. Okay, so it's denoted as U. So U equals 1.661 to minus 27. So if you want to attempt that, you should be able to do that. So it's going to be E equals mc squared. So we've got the mass, 1.661 times 10 to the minus 27, multiplied by 3 times 10 to 8 squared, which is 9 times 10 to 16. So that'll give us it in joules. So that is 1.4949 times 10 to the minus 10 joules. So to get that into electron volts, you should know this from year 12. We're going to divide that number by 1.6 times 10 to the minus 19. So that gives you a rather big number, but that's electron volts and you want mega electron volts, so you need to divide it by a million, or 1 times 10 to the 6. Or you could just divide by 1.6 to the minus 13. Alright, so that gives us 934 4.3 MeV, which is slightly off, but close enough. If you use more accurate numbers for the constants, I'm just going to switch to another PowerPoint, one sec. You actually get 931.5 MeV. So it's a useful unit to remember. We always work in units of U and MeV instead of always converting to joules and kilograms. That is on the data sheet, all right, if you want to find it. So 1 U is 931.5 MeV. Right, so a bit of information on this one. You might want to take some notes. Well, you will want to take some notes. So nucleons, remember, is the stuff in the center, in the nucleus, the protons and the neutrons. So suppose all the nucleons in a nucleus were separated from one another, removing each one from the nucleus in turn. You're going to have to do work, and you've got to overcome the strong nuclear force and separate each nucleon out from the others. So the potential energy of each nucleon is therefore increased when it's removed from the nucleus. And this is the binding energy of the nucleus. So it's the work that must be done to separate a nucleus into its individual or constituent neutrons and protons. That's the definition if you're asked. So when a nucleus forms from separate neutrons and protons, energy is released as the strong nuclear force does work pulling the nucleons together. So the energy release is equal to the binding energy of the nucleus, because energy is released when a nucleus forms from separate neutrons and protons. And the mass of the nucleus is less than the mass of the separated nucleons. So take helium, for example. So helium's, standard helium's 2 protons, 2 neutrons. If you measured the mass of 2 protons and 2 neutrons all individually, and then measured the mass of a helium nucleus, they'd be slightly different. And that difference in mass is called the mass defect. And that mass defect is where the energy comes from. So if you are, fusing a nucleus together or undergoing fission, the mass defect is where the energy is released. And obviously we utilize that energy. Well, the sun utilizes fusion, or a star, and we utilize fission reactions in nuclear power stations. So it's a small difference in mass, but when you've got enough of it occurring, you end up with large amounts of energy. So what we've got here is an example. So you could do this one. These U values are on your data sheet as well. So proton mass is 1.00728. Neutron mass 1.00867. So it's calculate the mass of a potassium atom. So what I want you to do is do the constituents. So we're going to pause and attempt that. So we get the total mass, as obviously we've got 19 protons and then 21 neutrons in that potassium atom. That gives a total mass of 40.32039 U. Yes, you have to use that amount of figures. You'll see why. So the actual measured mass is 39.9536 for a potassium 40 atom. So there's obviously a difference there. That's what I was touching on earlier. So the difference, if you subtract them, you're going to get 0.3667 U of missing mass. And that's the mass defect. So when nuclei are joined together, the total mass decreases. It's converted into energy and then released. Right, so worked example. You can have a go at this one if you want, but I'm going to take you through it anyway. So we've got polonium isotope, polonium-210 emits alpha particles and decays to form a stable isotope of lead. Write an equation for this process. All right, so that's pretty straightforward. So we've got polonium-210, so 210-84. And that decays into lead, so Pb20682. Plus an alpha particle, 42. So what we want to do is calculate the energy release in MeV in joules. Now the joules thing you don't typically have to do. I just thought I'd put that in for some extra practice. Because we always deal, really, for these kind of things in MeV, mega electron volts. So what we need to do is look at the masses and get the mass defect, the change in mass. So we've got the mass of the polonium-210, we've got the mass of the lead, and we've got the mass of the alpha particle. So obviously we're going to do before equals after. So you want to do that one and then subtract these two. So thereafter. And there'll be a slight difference in mass. And that's the mass defect, and that mass defect will turn into energy or convert into energy. So 209, we're going to do two. That's annoying when that happens. So 209.98286, and then subtract the 205.9744653. I know this is a bit laborious. And also subtract the mass of the alpha particle, so 4.001506. And that will give us a rather small mass defect of 6.8887 times 10 to the minus 3 U. Right, so to get that in MeVs really quick, if you remember what we wrote down earlier, so U value is 931.5 MeV. So if you multiply that by the mass defect, that will give you the energy released in mega electron volts, which comes out at, so energy in MeV, 6.42 MeV. Convert that to joules, so that's your 12 work. So first of all, you want to convert it into electron volts. So multiply by million. Let's get it into electron volts. So 1 times 10 to the 6. Then multiply by 1.6 to the minus 19. So it gives you the energy in joules. 1.03 times 10 to the minus 12 joules. Okay, hopefully you found that all right. Right, so let's do a few questions. So for each one of these, if you want to pause it and have a go. So this one should be quite straightforward. So nuclear binding energy is the energy required to overcome no, it's not electrostatic. Remember, it's strong nuclear force. Energy equivalent to the mass of the protons, that's just nonsense. C is nonsense. D, the energy equivalent of the difference between the total mass of the individual nucleons and their mass when they are contained in the nucleus. So obviously, you should have got D for that one. Right, if you'd like to have a go at this one. So a reaction shown below occurs when a proton and a deuterium nucleus fuse to form a helium nucleus. So we've got the energy released, so 5.49 MeV. And we've got the mass of everything in U. So you could convert them to energy and then convert back to mass once you've figured out what the helium is, the heavy helium. It's actually lighter, 3.2 helium. Or you can just convert the energy into mass. I would convert the energy into mass, I think, because everything else is already in mass, and you want mass, so that makes sense. So you got 5.49 MeV, so you could do 5.49 MeV divided by the 931.5 MeV, and that'll give you like the ratio of how many U it is. So the U value for the energy released is 0.00589371 U. So that's the energy. Then all we need to do is do this one plus this one and then subtract this one, and it should give us, or it will give us, the U value for the helium. So let's do that. So the proton, so at 1.00728, add the mass of the deuterium nucleus, which is 2.01, not 1355, and then subtract the U value because that's obviously on the other side. So if you do that, in fact, I'll just put that in, subtract this because I'm not writing it out again. If you do all that, you get 3.01494 rounded. So that's B. So that would be the mass of the helium-3 atom. All right, well done if you got that. Right, so this one's a little bit different. So mass difference or mass defect of the lithium-7 nucleus. So if you want to attempt this, that's good. Right, so we've got the actual relative atomic mass of the lithium nucleus, and what we need to do is add up what the constituents would be if it was separated, and then find the difference between them. So we've got 3 protons, mass of 7, so 3 protons, so you need to times that by 3, and then 4 neutrons, and then add them up, whatever they are. So the total mass of the protons is 3.02184, and the total mass of the neutrons, you should get 4.03468. If you add them together, so 3.02184 plus the 4, you'll get 7.05652. So that's the mass of the lithium nucleus. Not if they were all separated, it wouldn't be a nucleus then, it'd just be 3 protons and 4 neutrons. So the mass defect is going to be the difference between those two values. So the calculated separated nucleon value and the actual mass of the lithium nucleus. 7.01436. So that'll give you a mass defect of 0.04216. So that's D. Well done if you got that. So we'll look at another. So as you can see, these are quite repetitive, but they're obviously different questions, but they're very samey. There's an error on this one, so that's obviously deuterium. They've written that as 1, but that is the deuterium nucleus, so that should be 2-1. Right, so we've got a reaction. What is the value of Q? So we'll do it in terms of mass, and then whatever the mass defect is for the energy, we'll then convert that to MeV. So very straightforward. We've got the proton and the deuterium together, so we need to add these two, and then subtract the value of the helium nucleus. So 1.00728 plus 2.01355. Figure that out first. So that's 3.02083. And then subtract the helium nucleus, because obviously left-hand side and right-hand side. So subtract 3.01493. That'll give a change in mass, the mass defect of 5.9 times 10 to the minus 3 U. And then obviously to convert that into MeV, we can multiply that by 931.5 MeV, which is what 1 U is. 931.5. So that gives you 5.495, so 5.5 mega electron volts. If you got that, well done. Right, let's look at something called binding energy per nucleon. Right, so binding energy per nucleon, if I learn how to speak, binding energy per nucleon. So there's a graph here. Looks a bit complicated, but it's not too bad. Right, so it's all about nuclear stability. The binding energy of each nuclide is different. So as you can see, you've got nuclear number on bottom. So as nuclear number goes up, you'll get from hydrogen, not hydrogen, helium, or well, I suppose H2 would have a binding energy. Hydrogen 1 can't have a binding energy because it's just a single proton. H2 would be a proton and a neutron, so that would have binding energy. So it goes up rapidly. So as it says there, average binding energy per nucleon increases rapidly for light nuclei. That's why when you have nuclear fusion, you get ridiculous amounts of energy produced because of the steep change in energy. Iron is the most stable nucleus, which is part of the reason why, if you do astrophysics, normal sized stars can only produce elements up to iron. To get anything heavier than iron, you need tremendous force to push them together. That happens in a supernova. Average binding energy per nucleon decreases gently, as it's described, for heavy nuclei. So you do get a lot of energy from nuclear fission, but it's nothing compared to fusion. Right, the binding energy per nucleon of a nucleus is the average work done per nucleon to remove them all from the nucleus. Okay. And as we said earlier, it's a measure of the stability of the nucleus. So the more binding energy per nucleon, the more stable the nucleus is. So iron's got the highest value. Iron's the most stable. Right, so what I'll do, I'll show you how to do these just using questions. So this is like a walkthrough example. So we've got uranium-236 undergoes nuclear fission to produce barium, krypton, and 3 free neutrons. We're not bothered about the neutrons because they're on their own, so there's obviously no binding energy there. So what is the energy released in this process? Well, it's binding energy for each nucleon that's given in MeV. So what you need to do is to get the total energy is to multiply the binding energy per nucleon by the amount of nucleons. So that intuitively should make sense. So 7.5, there's 236 nucleons. This one, there's 144 nucleons, and the last one, there's 89 nucleons. So the uranium turns into the barium and the krypton. So what we need to do is the uranium, and then subtract the barium, subtract the krypton. So the calculations are 7.5 MeV per nucleon multiplied by 236. And then we've got 8.3 times 144, and 8.6 times 89. And what you're going to do is the top one, and then subtract these two from the top one. So the top one, so obviously if it's binding energy per nucleon and you multiply through by nucleons, you're just left with MeV. So that's 1770 MeV. And then you've got the 8.3 times 144, which gives you 1195.2 MeV. And then the final one is 8.6 times 89. So that's 765.4 MeV. And what you want is the difference between the top one and then subtract both of these. Or other way around, it doesn't really matter. You just want the difference. And if you do that, you will get 191 mega electron volts. Right, let's try another one. Right, so this one. So the graph shows that the binding energy per nucleon varies with the nucleon number. So that's the graph that we looked at earlier. So what is the approximate total you might not be able to see that very well, but it's 184.74. So you can attempt to do this on the screen, but it might be a bit tricky. But essentially what you need to do when you get a question like this is you go to 184, which is, I don't know, somewhere there. This will be, your answer might not be perfectly right, but it'll be close enough to know which one it is. So that goes to there, and then I want to go across and get the binding energy per nucleon, which is just under 8. You could probably use 8, it'd be absolutely fine. In fact, I will use 8. So what we've got is the binding energy per nucleon, which is 8 MeV per nucleon. And then we're going to multiply by the number of nucleons. So we've got 184 nucleons. And as you can see, nucleons will cancel, and we'll just be left with total energy in MeV. So that will give you approximately, obviously it's approximation, 14, only because the reading graph, 1472 MeV, and it wants it in joules. So times it by a million to get it into electron volts, and then convert it into joules. So times that by a million to get it into electron volts, and then multiply through by 1.6 to minus 19. And that gives us, so on my calculator, 2.36 times 10 to minus 10 joules. So you press engineering button on your calculator, it'll put it into pico, which is minus 12, and it gives us 235.5, 236 picojoules, which is close enough. It's going to be D. You probably, if you use a ruler in your exam, I know I used 8 just to make a point that it'd be fine. But if you're around the correct area, correct region, you'll get the correct answer. All right, let's do one final one. Right, so this one we've got the mass of a beryllium nucleus. So we've been given the relative atomic mass, which is 0.01473 U. And we want to know what is the binding energy per nucleon. So first of all, we're going to need the binding energy. So remember, for these ones, we need to calculate how many U it is if we had all of the constituent nucleons separated out individually. So we can do that. We've got the information for that. So we've got 4 protons, so we need to times that by 4. And then atomic mass is 7, so we've got 3 neutrons. So if you calculate both of those, add them up, and then subtract the actual relative atomic mass, that will give you the mass defect. Okay, so let's do that first. So that top one is 4.02912 U. Second one, 1.00867 times 3. So that one's 3.02601. Add them together. We get the mass of the constituents, so if you separate them all, to be 7.05513. So we want the mass defect, so we need to do the difference between what they are individually subtracted by the actual relative atomic mass. So you're going to subtract 7.01473. And that gives a mass defect 0.0404 U. So remember, we can convert that into mega electron volts, so it's given us this one, slightly different from what you might have on the data sheet. So the 0.0404 multiplied by 931.3 mega electron volts. So that gives us an energy of 37.62452. I'll just round up to 5 MeV. And obviously it wants mega electron volts per nucleon, so you need to divide by the number of nucleons, and beryllium's got 7. So if you divide that by 7, that will give you 5.37 MeV per nucleon, which will round to 5.4. It's a bit of a long one, that, but quite a bit of content, loads of example questions. Hopefully you found that alright. Thanks for watching.